Okay, this lesson is 11.1. We are on parametric calculus. The main goal today is to figure out the similarities between parametric calculus and our rectangular calculus that we've been learning all along. So just keep in mind that parametric is taking a rectangular equation and splitting it into two separate equations in terms of time. So x is a motion in terms of looking at the motion, the horizontal motion in terms of time, and y is looking at the vertical motion in terms of time. So when you look at it this way, then you can look at the particle going in both vertical and horizontal direction instead of just one way, okay? All right, so here it reminds you of the derivative of a parametric equation. You take the separate parts of the parametric equation, take its derivative, and then you divide dy over dt over dx over dt. That will give you the derivative of dy over dx. For the second derivative, it's a little bit more convoluted. You actually have to take the derivative of this previous derivative, and then that will be your y prime, and then take that divided by the original dx over dt, and that will give you your second derivative, okay? All right, so area under the curve in parametrics works exactly the way like it does in rectangular coordinates. So keep in mind that when you were doing your integral for rectangular coordinates from before, it's really here, this function, here's your f of x, and you have this region from A to B. And what you're essentially doing is you're really just adding up rectangles underneath so that you can fit perfectly under the curve, so you can have the exact equation, you can have the exact area. So the height of the rectangle is your function, and the width of your rectangle is really your dx, and that will give you your integral, your area under the curve. Okay, so for parametric, it's almost exactly the same, where your height here is your y function, and then your width is your dx, but then dx needs the derivative of the x component. So you gotta take the derivative, so g prime of t, and then that's your dt. All right, so for your area under the curve here, you can go ahead and work this out following the formula given to you here. The area under this curve of this parametric equation will be from 1 to 3 of your y function, that's your height, so 2t cubed plus 2 times your dx, so then you got to take your derivative of your x function here, and that would be your 6t minus 2 dt, and then you plug that all into the calculator, and that will give you exactly 540.8. All right, so at this point, you can go ahead and use a calculator for this integration part, because the idea is to see if you can set it up, not to see if you can actually value the integral. So we can use the calculator to kind of take care of the busy work in that portion, okay? All right, arc length from rectangular coordinates. Remember, it was the integral of the square root of 1 plus f prime, so it is the derivative of your function, right? So now, because you have two parts to your equation, the arc length now is defined as an integral from a to b, square root of the x component derivative squared, and then the y component derivative squared, right? Now, sometimes your parametric has these like really interesting graphs where it actually crosses itself. So if a parametric crosses itself like this, like kind of like a polar coordinate, polar graph here, you just need to find where it crosses itself and then use symmetry to find the arc length of half of it and then double your answer. So that way you don't have to do the whole thing. The only trick is you have to figure out where it crosses itself and then use that to double your answer. Use that as your interval limit, and then you can double your answer for your arc length, okay? All right, so for this part, find the arc length of this. So for me, I see my x component is cosine cubed t and y is sine cubed t. For me, I would actually do the derivative separately here so that it's not so much work all at once, right? So I go dx dt, don't forget your chain rule, 3 cosine squared t times negative sine t. And then dy dt is going to be 3 sine squared t cosine t. All right, now I can put in my equation for arc length. Arc length will be from 0 to pi over 4, square root of 3 cosine squared t times negative sine t, the whole thing squared, because that's my the derivative of the x component squared, plus 3 sine squared t cosine t, the whole thing squared. That is your the derivative of the y component squared, right? Now, You are welcome to put this in the calculator at this point, but this is kind of messy. So the suggestion is to actually clean this up. And most of these clean up really, really well. So that actually you want to put the cleaned up version into your calculator, and that will make it a lot easier. So if you clean this up, right, by actually squaring everything, you get 9 cosine 4t sine squared t plus 9 sine to the 4th t cosine squared t, square root the whole thing. Do a little bit of factoring, right? See what they have in common. You will see that they have 9 cosine squared t sine squared t in common, and that, after factoring out, gives you a lovely sine squared t plus cosine squared t, and we all know that is 1, right? So this is a big fat 1, so that cleans up really nicely. And what you have factored out are perfect squares. So really your integral becomes 0 to pi over 4, 3, cosine t sine t dt. Okay, now you can use u sub at this point because you can see this is a very good u sub problem, or you can plug it in a calculator, doesn't matter, but in the end your answer should be 3 over 4. Okay, all right. So before we move on to the last one, sometimes in other this arc length is used in other formulas, so we just call it the arc length differential to make it a little bit shorter to work with. So we just call it ds. Again, you will see that it pop up in the next part of our notes here. We're doing surface area. Very similarly to surface area for rectangular coordinates, that your formula is 2 pi times the function and times the arc length. Same thing here for parametrics. It's 2 pi times the function times the arc length differential, which is what we just talked about, right? So the only thing to remember is if you're revolving it around the x-axis, you are multiplying by the y component of your parametric. If you're revolving it around the y-axis, you are multiplying by your x component of your parametric equation. Okay, all right, so let's see. Find the surface area of the curve if it is around the x-axis from 0 to 2 pi. So your surface area is going to be integral from 0 to 2 pi, and because this is about the x-axis, I'm going to use my y component, so 1 plus sine t, okay? And now my surface area, arc length differential. So x component, the derivative of x component is cosine, the x component is cosine t, the derivative of that will be negative sine t, square that, so negative sine t squared. And then the y component is 1 plus sine t, the derivative of that is cosine t squared dt, and you can see, right, this becomes sine squared t plus cosine squared t, and once again this is a lovely 1, so that goes away nicely. So now I'm going to take my coefficient out, 0 to 2 pi, integrate 1 plus sine t dt. Again, you can use a calculator, but if you do this by hand, you actually get the exact answer rather than the decimal estimation. So you get 2 pi, and then t minus cosine t evaluated 0 to 2 pi. So it gives me 2 pi, plug in the 2 pi minus cosine of 2 pi, minus 0 minus cosine of 0, right? So then what do we get? We get 2 pi times 2 pi minus 1 plus 1, my final answer of 4 pi squared for my arc length, okay?